We're finally back with episode 15 of the MiSTer Retro Wolf Core Dev. In this episode, we'll discuss CPU interrupts, how that fits in with the control for our game, and then finally, we'll look at what we've changed in the code to make it all work. In the last episode, we got to the point where our game booted into the RAM test routine and now includes the tile map graphics and bullet sprite graphics. The game hit a snag and just freezes though, and this is because it's looking for the correct hardware to be implemented, and that is the interrupt hardware. In this episode, we'll learn what that is and how it's used for input and output in the Tank Battalion game. So what is a CPU interrupt? Well, here we can see two pins going into the 6502 CPU that we're using. One is the IRQ and the other is the NMI. The IRQ is the interrupt request and the NMI is the non-maskable interrupt request. Both are active low, which is why they have the bar over them in the diagram. Both interrupts trigger the CPU to hold what they're doing and execute a part of code that is located in the ROM when the right conditions are met. For the IRQ interrupt, the diagram here shows what happens. First, the CPU completes any instructions that have already been started. Then there are some operations such as pushing the last program address executed onto the stack, which is a filing area in the CPU. This is done so the CPU can safely return to the code after the interrupt has been completed. Eventually, after a few cycles, the CPU looks at the interrupt vector address, which for the IRQ is at the location FFFE and FFFF. We've seen something similar after we reset the CPU, where the reset vector looks at the address in FFFC and FFFD to get the location of the beginning of the program. In this case, it gets the address at FFFE and FFFF. For the Tank Battalion game, this is address 7C6C. So once the interrupt is triggered, it goes to this address. We'll see what this does in a bit. The IRQ interrupt must be turned off by ensuring the trigger on the IRQ pin returns to the high state. The IRQ interrupt can be turned off or ignored if we set a specific interrupt flag in the CPU. The next interrupt, the NMI or non-maskable interrupt, cannot be turned off. This interrupt is triggered from the NMI pin going low, but it is the input from the high to low that triggers it. If it stays low, it will not affect the operation of the CPU. In this case, the interrupt vector is at the address FFFA and FFFB. So the value there is the start of the interrupt code. So let's have a look at how the interrupts are used in the game. This diagram is the schematic of the game, with only the relevant parts for the interrupts or those related to the game controls showing. We've got the CPU, the 6502, with the IRQ pin and NMI pin, and also the circuitry in this lower area that's used to select the correct part of memory to address, or to address the input or output peripherals, using the 74LS42 chip that we've seen before in the addressing episode. On the right hand side here, we have the 3 chips that enable input interfacing, and the chips to the left here that allow output interfacing. The most basic fact is that IOQ pin is triggered by the 5F flip-flop on every input of the clock cycle 16V. There is then an INTAC or interrupt acknowledge pin that the program can trigger to reset the interrupt once the required code has been run. The next thing is that the NMI pin, the non-maskable interrupt, is triggered by a combination of the NMI on and the V blank. This NMI on comes from an output pin of these chips here. One point to note is that these schematics, as far as I can tell, the circuit either uses the 4099 chip or the 74LS259 chip. I'm not sure why they put both in the schematic, but looking at the actual photo of the circuit board, we see only the 259 present. From what I can tell, the functionality is exactly the same, except that the behavior of the reset pin is reversed. This 259 chip is a latch chip, so the NMI can be latched to be on and then is triggered every V blank. We'll see that the controls are then checked every V blank by this non-maskable interrupt. So these chips, the 259 and 251s, are essentially creating a way to select or read the outside peripherals, mostly controls, by allowing them to be addressed by the CPU. This figure is a recap of the addressing for both inputs and outputs. For inputs we have 3 groups, driven by the 3 LS251 chips. And that is the in0, which can see the joystick direction buttons, fire buttons, and also some coin input buttons. This is fetched using the address 0C00 to 0C07. At 0C07, there's a service switch that can be used for functions in the test mode. Next up we have the in1 group, which is mostly not used, but has the important function input buttons of player 1 start and player 2 start, and the test mode toggle switch. These are fetched using the address 0C08 to 0C0F. The final input group is the dip switch group, that sets things like how many lives you get, how many coins you need for a game, and what the bonus is in the game. Those are fetched by looking at the address 0C18 to 0C1F. Now for outputs we have the group on out0 and out1. Out0 doesn't have any relevant hardware for us, mostly related to lights flashing in the arcade machine. And out1 has triggers for sound, but also changing the interrupt modes. For example, we can't use the controls while the machine is booting up, doing its internal checks. These outputs are addressed using the addresses 0C08 to 0C0F for out1, and 0C10 for the interrupt acknowledge, and 0C18 for the watchdog reset. As we saw in the previous episode, the watchdog reset circuit is reset every so often to ensure the game functions okay without needing to unplug it from the power. Let's look at how the LS251 works to read the inputs of the game. In the schematic we see that the dip switch input, we have the batch of microswitches here, and then there is the 7F chip. We have a select pin, which is active low, connected to the dip switch selection address. We have 3 inputs ABC, which allow the correct control to be addressed, and then each dip switch is connected to an input pin 0 to 7. Depending on the selection address, the output Y is carried through from the relevant input. This is then connected to D7 pin that goes into the CPU, which is the highest data pin. The functionality is the same for all 3 groups of input pins. This 74LS251 is actually called a 3-state 1 of 8 line data selector, pretty obviously because it can choose 1 of 8 pins to output depending on the input address, from the 3 address pins. The function table here shows that depending on which pins of A, B and C are high or low, we select the specific input pin to output. But of course the chip select pin needs to be low, otherwise there's no output from the pin at all, which is what Z means. The diagram below shows a quick example of the address pins changing and how it selects the various data from the input. The output can only be 1 or 0, of course, so not too much to see here, just that it works when the selector pin is low, but doesn't when it's high. Now let's see how the output chip works, the 74 LS259. This is an 8-bit addressable latch. Looking at the schematic, we see for out 1 we have a write enable pin, which, the same as the select pin, needs to be low to be active. We again have pins A, B and C to create an address, and then we have an input D which can either be high or low, which comes from the D0 pin or the lowest data pin from the CPU. It then selects an output pin based on the address it receives. So essentially it's the exact opposite of the LS251 chip. Looking back at the chip info, we see that once again the E pin needs to be low to function, but there is some slightly more complex functions since the chip is a latch. The pin C or clear is used to change modes between a demultiplexer or an addressable latch. What this means is it either remembers the state of all the outputs, or it's just selecting one of them on its own. The diagram below shows that when the NC pin is low, clear is active and the output is just selected by the input address. But over here, when the NC pin is high, then the output pin remembers the trigger state and stays that way. This is how we trigger the NMI state to remain on for the game to allow the controls to be used during the certain parts of the game. So the Tank Battalion game has a number of states during running, and we'll now go through each state to see how the program and hardware is interacting, and how the interrupts and controls are interrogated during each stage. This figure shows the 7 main states. We have the first one, which is the RAM test cycle. During this time, it's not just a nice picture that gets plotted across the screen with these old arcade games. The program is placing a specific pattern through the entire memory map, including the video RAM, and that's why we see the patterns. It then reads back the results of the stored memory to see if it matches. If it doesn't, there's a good likelihood that a memory chip is bad, and therefore it can tell you which one to change. The second state is the test pattern grid. This is useful for lining up the screen in the cabinet to ensure the whole game is showing. The third state is the beginning of a tracked mode. It shows a running count of the possible points you can score, and then the fourth state is the full attract mode, showing a game running. This then loops back to state 3 when it's finished. If the coin button is pressed, or in the arcade if a coin is inserted into the mechanism, then the fifth state shows, which tells you how many credits you have. This screen is now fixed until you start the game by pressing the Player 1 Start or Player 2 Start buttons. If you do press the Start button, you get a short screen, screen 6, telling you to get ready to play. Then finally we get the seventh state, which is the game playing properly with input needed, to control the tank around the maze and to shoot the enemy tanks. To understand how the game works, we'll take a look at each state to see what the interrupts are doing and what the CPU is doing. To do this, I've used Signal Tap to record the state of specific pins in the FPGA design. I've clocked it as Phi2, which is the CPU clock speed. Therefore, we get a nice view of the CPU address that it's looking at. The pins we're going to be looking at are the 3 buttons on the I/O board on the MiSTer. I've hooked one up to the reset, I've hooked one button up to the coin input, and one up to the start player 1. In addition, I'm monitoring the interrupt pins on the CPU and also looking at the addressing selector pin on the 74 LS42. With these few pins, we'll get a good feel for what the hardware is doing during each stage of the game that we just defined. For this first state, the hardware doesn't want any interaction, so we see that the NMI pin is high. Interestingly, the IRQ pin is low, but it's not responding to it. The main feature is we can see that the watchdog reset is constantly triggering to ensure that the game does not reset. We can see that the address matches to what we expect, since 0C18 hex is the watchdog reset trigger. Now interestingly, the IRQ pin goes high and the system interrogates the dip switches. That is the highest pin of the F4 output. It reads it 8 times for the 8 switches that we have. The addresses, as expected, range from 0C18 to 0C1F. After the CPU receives the data from these pins, it can then set up the game correctly for the number of lives and so on. The test grid pattern goes back to no inputs, and then just has the watchdog triggering, and the NMI is high and the IRQ is low. In the first attract mode state, we have a few things going on. We have our first sign of the IRQ triggering regularly, and you can see lots of activity on the input-output pins. The most important of these is this little cluster during the IRQ going low. Now remember earlier that when there's an interrupt triggered, there is a specific cycle of activities that the CPU does. We can see in the diagram that the CPU is doing exactly that. We have the last operations completed, there's an address pushed onto the stack, and then the interrupt vector is read at FFFE and FFFF. We expect for an IRQ to read 7C6C, which it does, and it then jumps to the location for the part of the program dealing with the interrupt. The second plot below shows the main activity of this interrupt, which is to read the coin inputs and the start buttons. The important point from this figure is to see that the CPU sends an interrupt acknowledge signal that resets the interrupt on a hardware level, so the functions can be resumed. During the proper attract mode, we get a glimpse of how the game will operate. We see the NMI pin triggering for the first time during the VBlank period. The lower diagram shows how the CPU cycle happens with the non-maskable interrupt triggered. It's similar to the IRQ, but we have a different reset vector of FFFA and FFFB. The address it goes to for our game is 79 dB. If the coin button is pressed, we go to the state shown below. It's monitoring the system for the player start or another coin input, but not monitoring for game controls. Interesting, this increasing frequency pattern on the watchdog reset, etc. I think it's just related to a counter that's probably counting down or something. When the player start is pressed, then there's a short loop telling the player to get ready to play. During the game, the most important feature is during the VBlank period. The NMI and the IRQ go low and the system interrogates these 4 controls, this control, and then these 3 controls. The first 4 are the direction buttons from the joystick. This one on its own is the fire button, and then these 3 are related to coin insert code, which needs to be detecting a coin even if we're playing the game. It finishes with the interrupt acknowledge to come out of the IRQ mode. This is just showing proof that the addresses looked at are the controls, 2 of the 4 shown, and then the addresses related to the coin input. So with all that together, let's see the game launch and run through the sequence. Into the attract mode, then inserting a coin and pressing the play button to go into the game. Now we don't have our controls working, and for that we'll need the MiSTer framework, since we don't have a simple way to talk to the USB controller through the FPGA output pins. Of course we could rig something up, but then it wouldn't be the MiSTer project. We'll get that going with the controls in the next video. For now, let's take a look at what we've changed in the Verilog code to get the game to this point. If we go into episode 15 on the GitHub, we have the code for the CRT and for the VGA outputs. We'll only need this for this last episode, since the next time we'll have the full MiSTer framework, which will do both automatically. First, let's look at the TTL chips file. Okay, so I've added the two interface chips that we've discussed in the episode so far. We've got the LS251 first. As we've seen, it's got the CBA input, which takes in a 3-bit address, and we have a chip select pin, an 8-bit input and 2 outputs, Y and the opposite of Y, which is W. For the code, it's quite a simple always statement based on the inputs and a case statement. So if the S is low, we use the case statement to check the address in CBA. And based on that, we make the output Y the correct pin of input D. We make W the opposite of Y. If the selector pin is high, then the output pins are floating, which is denominated by the Z in Verilog. So not too much difficult there. The next one is the LS259. It's similar to the 251 as we've seen. We have a 3-bit input address called A. I've not been too consistent with labeling since we had CBA for the last one. Also, as inputs, we have the enable and clear pins, both active low, and the 1-bit input D. Finally, we have the 8-bit output Q. Once again, we have an always block triggered by the inputs. I excluded the address A since that will be changing all the time based on the CPU data input. It doesn't matter too much. We have a few different states based on how the chip operates, as we've already seen. The first is that if NC is low and NE is high, we have a clear situation with no enable. So that means that we set all the output bits to 0. Now if the clear is low and the enable is low and the input pin is low, then again all the output bits are going to be 0 or low. Now if we have a clear as low, enable as low but the D is high, we have a selector situation, whereby one output pin will be selected to be high and all the rest are low. And that depends on the address A. We have a default situation, but that should never be used since we always have a covered situation with the input address of A. If the clear pin is high and the enable pin is high, we have no change to the last situation of output pins. And finally, if the clear pin is high and the enable pin is low, we're in a latching mode, and the output Q is dependent on the input D for each address in A. That covers all the situations of the chip and allows our non-maskable interrupt to be latched to on when we play the game. The last file we've modified is the Tank B FPGA file, so let's take a look. First, I've added the input pins from the I/O board, the buttons for reset, OSD and user, which I use to input a coin and start the Player 1 game. This is just temporary for this episode. Then down below, since I've included a reset button, the reset to the circuit will either be the power on reset or the reset button. Here I've added the wires for the interrupt, the definition of the NMI input based on the NMI on and VBlank, which we saw in the schematics. Next we have the CPU inputs, and here I've changed the NMI input from always high, so turned off, to be wired to the previous NMI definition. So now the CPU can be interrupted based on the new hardware that we've added. This lower RAM area here has been updated to include both CPU input and bullet RAM output for the Sprite hardware. It's a dual port RAM, so these won't interfere with each other's operations. If we go down to the CPU data in definition, previously we had the selection of input data based on addressing for all the memory, but now I've added the 3 other inputs for the dip switches, the input 0 controls and the input 1 controls. Remember that the output of the interface chips were just changing the D7 highest bit of the data bus, so I have a variable for that bit in each input location, and the rest of the 7 bits are just set to 0 using a concatenation in Verilog. The CPU will only read that top bit anyway, so the other bits can be anything. After that, we just need to go to the instantiation of the peripheral chips, the 251s and the 259. The inputs are the lower 3 bits of the CPU address bus, and the selector pins for the chips are the in0, in1 and dip switch selector pins that are active low. The D inputs are a concatenation of buffers dip, in0 and in1, which are just set high, in addition to the control pins from the I/O board, the OSD button and the user button in this case. Outputs for the chips are set in Y and Q, which we saw feed into the CPU data in. And so that's it. Not too many big changes needed to ensure that the game now functions correctly. All we're missing now are the controls to play the game. As I said, for that we need the MiSTer framework, and at the same time we set that up, we'll incorporate using an MRA file that allows us to distribute the core without needing to include the ROM files, which of course are not legal to distribute. In the meantime, please note that there's now a working version of the game that includes the MiSTer framework on the GitHub. This will allow you to play the game, albeit without sound for now. It's going to be interesting to try and get sound working in this game. I'll be attempting to recreate the analog sound circuit in Verilog, so we'll see how that goes. If I can't get it working, we'll have to resort to using samples. So once again, thanks for joining me, and I look forward to next time where we'll talk all about incorporating the MiSTer framework.